let's go ahead and do our usual sound check before we get started. Sounds good. Can I see my hand? Yes, I can. Okay, looks like we are good to go. Let me go ahead and get rid of the headphones since I don't need them. So I did check the audio from last week and I noticed that it was a little bit lower, well, maybe more than a little lower in quality than what I'm used to. So I played around a little bit with the sound settings and hopefully this time it'll be better. I've put a little bit more distance between myself and the microphone, and my voice still picks up just fine. So I think I have the perfect setup this time. If not, I might need to tweak it just a little bit more. But one thing's for sure, based on my tests, it's definitely better than last week's audio. At least that was the case when I tested it with recordings. I don't know if it's going to be any different if I'm streaming it, but I guess we're going to find out. So yeah, the plan for today is to go over circular motion and planetary motion. So let me go ahead and take a look at my circular motion chapter in my book and see what we have to work with. What would be good for review? I don't want to go with the most standard uniform circular motion problem, so instead I think what I want to do is go with like a banked curve problem to start us off. Let's see where my banked curve problems are. Well, I have number 24, which I've shown to my students many times. Do I have a different one? Give me a minute to look around for it. Probably should have done this ahead of time, but with my schedule being as busy as it is, it's not something that I can always make sure to do. And besides, these meetings are supposed to be like, more, what's the term? Off the cuff, I guess. The whole point is not to really have a plan, but just kind of do a bit of exploring and see what we can find. Okay, I think this one might be good. It says a car rounds a banked curve where the radius of curvature of the road is big R, the banking angle is theta, and the coefficient of static friction is mu. Determine the range of speeds the car can have without slipping up or down the road. And then part B says what is the range of speeds possible if we actually assign numbers. Big R equals 100, theta equals 10 degrees, and mu equals 0.10, which apparently indicates slippery conditions according to the book. That one might be good, but before I dive into that one, I want to see if I can find some others. Well, it's not a banked curve problem, but it does look interesting, so I might want to go over this one that talks about escape speed from the surface of a planet. I'll have to remember that for later. I don't see any other banked curve problems here. Okay, so I guess it's just the one. Okay, we'll work with it. And it's nice that it's more of an expression problem, because we could use more examples of those. I mean, if you need practice with expression problems and you don't have that many in your book, then you have a really easy solution for that. Just do any problem in your book, but don't plug in actual values. If you're given the values for things, just don't plug those values in. And there you go, you have yourself an expression problem. Alright, so I'll read the problem again. It says a car rounds a banked curve where the radius of curvature of the road is big R, the banking angle is theta, and the coefficient of static friction is mu. Determine the range of speeds the car can have without slipping, and then calculate that range given a bunch of numbers to plug in. Maybe we'll do that part, maybe we'll skip on it, we'll see. Anyway, we are given a banked curve with a radius of big R. That's the top view of it, and then the side view is going to look like this. I'll draw it even bigger so I have more space in case I need to draw on top of it, which I most likely will. Okay, so if I'm looking at a car, let's say the car is over here. When we're looking at it directly from above, and let's say this car is here when we look at it from behind. So let's say this car is moving this way. From this perspective, we are looking at the car moving away from us, so into the page before it turns around and curves around. We need to go ahead and draw our force diagram. So forces acting on this car. This is the part that tends to trouble students because they expect it to work just like an inclined plane problem, but it doesn't. So we've got force of gravity straight down. We are not going to break it into components. We have a normal force that is perpendicular to the road. And then they said we have static friction, which can be either direction because they asked for the maximum and minimum speeds we can have. At the maximum speed, the car is about to drift outward. So if I'm looking at the top view, at its maximum speed, it's about to drift outward like so. And at minimum speed, it's about to drift inward if it goes any slower, like that. So at maximum speed, it would be attempting to move up the incline, in which case the force of static friction would be down the incline. And at minimum speed, it would be attempting to slip down the incline, in which case the static friction would be up the incline. So static friction can actually be up or down. Let's go with down for now. Let me do this in a different color so that I remember to remove it and replace it later. Actually, you know what I'll do? I'll draw two diagrams. So that's force of friction static that way, and then I'll draw the diagram again. Come to think of it, I forgot to label theta in the first diagram, so there we go. There's theta in our second diagram. And draw the back side of the car. This time I want the force of static friction to be up the incline. And draw my other forces, force of gravity and normal force. Force of gravity and normal force. Okay. In order for this car to smoothly go, smoothly probably isn't a very well-defined term. In order for this car to uniformly turn around this curve, it requires some sort of centripetal acceleration towards the center of this circular path. So the centripetal acceleration, at least at the moment when the car is right here, the centripetal acceleration would have to be this way. The centripetal acceleration would have to be this way. In order to have acceleration in a particular direction, you have to have a net force in that direction. So if you want your acceleration to be straight to the left, you need your net force to be straight to the left. You need a net force to the left, and the magnitude of that net force needs to be mass times centripetal acceleration, which is v squared over, in this case, it's big R. Okay. So that means I need to figure out which forces I have to the left and to the right. Not up the incline and down the incline. Those are not the directions that we want to use this time. Normally with inclined planes we use up and down. Well, I should say parallel and perpendicular to the incline as our coordinate system. And not the case here. Here we actually want to just use the traditional x and y coordinate system. I guess we would also, just for convenience, say that the x-axis points to the left this time as opposed to the right, just because of the way I drew it. But yeah, that means we actually don't need to touch the force of gravity. Force of gravity is already aligned with the y-axis, so it's good. It's these two forces, the normal force and the friction force, that need to be toyed around with. So let me go ahead and do some geometry to figure out how these break down. So if I draw some axes over there, I see that the angle made between my x-axis and my force of friction is equal to this theta over here. So that angle is equal to theta. Okay, and what about for the normal force? I guess my x-axis is going through the tail of it just fine. I'll draw another y-axis there. For that one, I have this angle over here is equal to theta, which means that this angle over here, I'll draw it in pink. This angle over here is 90 minus theta. And we can then say that this angle over here must be theta again. So that's theta, and this angle over here must also be theta because it forms 90 degrees with that pink angle. Okay, so that means that normal force times cosine theta would be the component of the normal force pointing straight up, and normal force times sine of theta would be the component of the normal force pointing to the left. Come to think of it, I also need to do something similar up here for the other case for friction. For normal force, it'll just be the same case as before, with this angle being theta. And for the force of static friction down the incline, that angle is theta. So yeah, I think we are already done with figuring out our angles. Okay, so since I want a traditional x and y coordinate system, I need to go ahead and break everything into x and y components, and I want only my net force, I only want a net force in the x direction. I need a centripetal acceleration that's only in this x direction to the left. I don't need acceleration in any other direction. So I want my net force in the y direction to be 0. My net force in the y direction had better be 0. Otherwise, this car would either start magically levitating upward, accelerating up and off of the road. That doesn't make sense. Or accelerating down and basically burrowing into the road. That doesn't happen in reality either. Unless the road is made of sand or something, we don't see that happening. So common sense dictates net force in the y direction must be 0. Okay, so with that in mind, let's go ahead and break these things into their components. What color do I want to use here? Actually, I don't think I want to draw any more on top of these. So what I'll do instead is, for this one, I'm gonna draw the other vector components off to the side. Would that be a good idea? You know what? I'll draw them using dotted lines. So I'll do this. That's force of friction static times cosine of theta. And then that is force of friction static times sine of theta. I'm going to do something similar over here. That will be force of friction static times cosine of theta. And yeah, I don't have enough space for it here, do I? If I take the component pointing straight down, that would be, where do I even want to draw it? Or write it? Should have gone with a bigger diagram or found a better place to write it all. I guess I'll write it over here and just point to it. Force of friction static sine of theta. There's that vector right there. Not the cleanest looking diagram, but it'll have to do. Okay, that's for our friction components. Now for our normal force components. Vertical component is going to be normal force times, it's adjacent to this green angle, so it's normal force times cosine of theta. And the component pointing to the left, I don't even have the space to draw it. Yeah, that doesn't look very good. Well, that's okay because I have an opportunity to draw it more clearly on the second diagram. Yeah, I'll just draw it here, and here we can call that normal force times sine of theta. Or you can do normal force times cosine of 90 minus theta. It works out to the same value either way. But yeah, that's what I wish I could have written up here. It even looks horrible. It looks like it's tilted upward at an angle when it's supposed to be horizontal. I messed that up really badly. But it's okay as long as you know what it's supposed to look like, and I guess my advice here would be to draw a separate diagram for your components, or draw a much bigger diagram than what I have so you actually have room to write all the details. Anyway, if we go ahead and look at, I'll start with the first diagram. My forces in the y direction need to cancel out to 0, so I would have to do normal force cosine theta upward minus downward we've got the force of friction sine theta and the force of gravity. So minus force of friction sine theta. So force of static friction, at least when it's at its maximum value, is going to be equal to the normal force times the coefficient of friction. So I can go ahead and write that as mu times normal force, and then that times sine of theta. So that takes care of our downward static friction component. And then also downward we've got the force of gravity, so minus mass of the car times g. Alright, that takes care of net force in the y direction for the first diagram. We'll do the second one in a bit. Net force in the x direction for our first diagram. We have force of static friction cosine theta to the left, and we also have the horizontal component of the normal force, which was normal force times sine theta. So I've got normal force times sine theta, taking left to be positive here. Normal force times sine theta plus static friction cosine theta. Static friction is coefficient times normal force. And then that times cosine of theta. Alright, now let's go ahead and write similar equations for the second scenario. You probably won't be surprised that the equations are similar, with the only thing changing that changes being the direction of the friction components. So net force X equals m v squared over r, and net force Y is still 0, And I guess I want to tell these two apart by determining which of these V's is the maximum versus the minimum V. So let me go ahead and actually indicate that now. So if the static friction is pointing down the incline, then the car is moving fast enough that in the absence of friction, it would be drifting outward like so. Because in the absence of friction here, the friction is actually adding to your horizontal force. It's adding to your centripetal force. It's adding to the force that tries to keep you in your circular path. So if you remove it, then, well, you've got less force pulling you left, which means you're either going to have to turn in a wider circle or just drift away. So that indicates that in this scenario, you are at the maximum speed. And over here, if you're driving too slow, then you'll start to drift inward because your horizontal acceleration is greater than necessary to keep you in a circle of radius big R, so you'll start turning in a circle of radius less than big R. So that must be the minimum speed. Very important to distinguish between the two so that we don't feel tempted to set this equal to what I'm about to write over here. So what I'm about to write over here, I guess we'll do horizontal first this time. Horizontals, I want to do left minus right. Again, I'm using left as my positive direction here. I've got normal force sine of theta to the left, same as before. But this time, force of friction cosine theta is to the right, so minus coefficient of friction times normal force times cosine of theta. Okay, vertically, we still want everything vertically to cancel out, so force is up minus force is down. Upward, we've got normal force cosine theta is pointing up. Normal force cosine theta, so same as before so far. We also have the static friction force sine of theta pointing upward. So that's plus coefficient of friction, normal force, and sine of theta, and then minus mg. Mg is still down. All right, so now what? Our givens, we were not given the mass, so that needs to go somehow. We were given radius of the turn, we were given theta, so that we can keep in our final expression, and we were given the coefficient of friction, and the value of g is just a universal constant, so we are allowed to use that. We are allowed to have that in our final expression, and it'll be just fine. All right. So what I want to do then is find an expression for the normal force, because that's a variable we introduced. It can't be allowed to remain in our final expression. And for the mass, we're just going to hope that it cancels out, as it often does in physics problems. So let's try and get the normal force. I want to use my vertical equations first. So it looks like what I can do is I can add the mg over to the zero side of each of those equations, and then I can factor out the normal force from the terms that remain and divide over what's left. And that will give me an expression for the normal force. Let's go ahead and see what that does for us. So instead of writing two expressions, I'm going to use plus or minus notation instead. So if I add mg over to the left, I'd have mg equals normal force times, and then in parentheses, cosine theta, and in one case it's minus, in the other case it's plus. So I'm going to say cosine theta minus or plus, and then I have the coefficient of friction times sine theta, mu sine theta. And then from there I can solve for the normal force. Normal force equals, should probably write it over here actually. Normal force equals mg divided by all that stuff. Mg over cosine theta minus or plus mu sine theta. And if you're wondering why I'm using minus or plus as opposed to plus or minus, I think you'll see the value in that in a minute. It just helps make our notation a little bit more compact. Anyway, I can substitute this into the horizontal equations. So for the horizontal equations, I'm going to have mv squared over r. I'm not specifying whether it's v max or v min. Mv squared over r is equal to, I'm going to factor out normal force, and then I'll have sine theta plus or minus coefficient times cosine theta. So the normal force that I have factored out, I can just write that as what I solved for up here. I can just write that as mg over cosine theta minus or plus mu sine theta. Okay, so that's the normal force, and then multiply that by sine theta plus or minus, multiply that by sine theta plus or minus mu cosine theta. And I didn't leave enough room to close my parentheses. So I can cancel the mass on both sides, which is good because otherwise we would have to figure out another way of dealing with that. And I can rewrite my expression. I guess I'll have enough room for it here to write it more nicely. V squared over r is equal to g times, I'm going to move all this stuff into the numerator, sine theta plus or minus mu cosine theta over cosine theta minus or plus mu sine theta. So the reason that I chose minus or plus up here is going to become clear with this. So the idea is If you choose the plus in the numerator, you have to choose the minus in the denominator. If you choose the minus in the numerator, you have to choose the plus in the denominator. So if you choose the top one here, you choose the top one here. If you choose the bottom one here, you choose the bottom one here. That's basically the distinction between plus or minus versus minus or plus. It helps with cases like this so that we don't have to write two equations. Otherwise, I would have had to write V max squared over R equals G, and then taking the plus in the top and the minus in the bottom, and then separately write V min squared over R equals, well, the opposite, G times, take the minus here and the plus in the denominator. But this is just a more compact way of writing all of that. So yeah, we basically have our expression for V. All that's left is multiply by R and take the square root, which is easy enough to do, so I'll spare you having to do that. Actually, we might have to do it anyway if we want to plug in the numbers, because in part B it says, what is the range of speeds possible if big R is equal to 100 meters, theta is equal to 10 degrees, and the coefficient of static friction is equal to 0.1, which is pretty low, which is probably why they say in parentheses that these are slippery conditions. I guess we can plug in some numbers just to get a real sense of it. Let's do that on a separate sheet. So if R is equal to 100 meters, theta is equal to 10 degrees, and what did they give us? And the coefficient of friction is equal to 0.10. Find V max and V min. So V max equals the square root of RG times sine theta plus mu cosine theta over cosine theta minus mu sine theta. Did I copy that right? Yep, sine first, sine mu cosine, cosine mu sine. Yep, I got it. And then similarly, V minimum will be the square root of RG times sine theta minus mu cosine and cosine theta plus mu sine. I guess another way you could tell which one is which if you didn't figure out, in terms of when friction is absent, would the car drift outward or inward relative to the original circle? I guess you could determine it mathematically if you didn't want to think about the physics, just by the fact that over here you have an addition over a subtraction. Bigger numerator over smaller denominator is a bigger number overall, versus a subtraction over an addition is a smaller numerator divided by a larger denominator. So obviously this is the smaller number from the math. So yeah, you could determine it from just the math and how fractions work if you couldn't be bothered to figure out the physics, or if you just felt too overwhelmed by the physics. This would be an alternative method of determining which one is which. Anyway, plugging in numbers, let me go ahead and bring out my calculator. So square root of 100 times 9.8 times fraction button. I've got sine of 10 degrees. Is my calculator in degree mode? Yes, it is. always check your calculator and make sure whether it's in degree mode or radian mode, especially if you're also taking calculus or pre-calculus in the same semester that you're doing physics, or same year for that matter. Anyway, sine of 10 degrees and plus mu, which is 0.1, times cosine of 10 degrees over cosine of 10 degrees minus mu, which is 0.1 again, times sine of 10 degrees. And if I put that into my calculator, I'm getting 16.6 meters per second. 16.6 meters per second. Okay, what about V minimum? So if you know how to use the copy feature of your calculator, you can just copy your previous input and edit. The only thing that needs to be changed is you need to edit the minus into a plus and the plus into a minus. So you don't have to type it all out on your calculator again if your calculator allows you to actually press the up button and highlight previous inputs. You don't have to retype the whole equation again, just edit the parts that change and keep everything else the same, and I'm getting 8.6 meters per second. All right, not bad, and I guess if you live in the United States, you can consult Google and ask for the conversion rate between meters per second and miles per hour to see what the speed limit should be over here, at least under slippery conditions. I'm actually not sure. Meters per second to miles per hour. I'm not sure what that conversion would be off the top of my head. Let me calculate it real quick. I know a mile is 1,609 meters approximately, so if I did 1 meter per second times, let's see, every 3,600 seconds is 1 hour, so times 3,600 and divided by 1,609 meters. That's a conversion factor of 2.237 miles per hour for every meter per second. So if I took 16.6 times 2.237, that's 37.13 miles per hour for this one, about 37 miles per hour, and the other one is about half of that. So yeah, that's actually slower than when you're not on the interstate. Well, I guess it depends on whether you're on like a main road or if you're in a neighborhood. In neighborhoods, the speed limits are still even lower. But they did say this was under slippery conditions, so yeah, this could still be a highway. Anyway, let's go ahead and look at the other couple problems I wanted to look at. I'll deal with that escape velocity one later. Before that one, I want to do this one, which can be a bit tricky for students who aren't very good with their trig. Actually, even if you're good with your trig, it's more about just, I guess, observational skills and being able to recognize a certain algebraic relationship when you see it. It says a 0.5 kilogram ball that is tied to the end of a 1.5 meter light cord is revolved in a horizontal plane with the cord making a 30-degree angle with the vertical, and it tells you to look at the figure in the book, which we can look at in a minute. Determine the ball's speed is the first thing they ask. Then part B is asking if instead the ball is revolved so that its speed is 4 meters per second, what angle does the cord make with the vertical? And then part C, if the cord can withstand a maximum tension of 9.8 newtons, what is the highest speed at which the ball can move? I think it might be that second one that's the hardest to do, but we will have a look at it. So in terms of the figure, here it is. Basically a person swinging something in a horizontal circle, but the string itself is actually being held at an angle with the vertical. So that's something to watch out for. It adds a little bit of complexity to this problem. Well, maybe not just a little bit. So I'll go ahead and try to recreate the drawing over here. Not sure how good my 3D drawing skills will be, but I will try, and I'll try to draw it on the right side this time so that I have more space on the left to actually write stuff. So ball on a string, and then something like that for the circular path. There's the center of that circular path, and there's the point at which the ball is actually tied. For the mass of the ball, I'm just going to say m. And for the angle, I'm just going to call it theta. I'm not going to write the numbers that they actually gave us because the numbers keep changing between part A, B, and C. So I'd rather just keep them in terms of their variable names. There is the length of the string. I guess that's a constant, but for now, I'm going to call it L. And then there's the radius of the circular path, which I'm just going to call R. And I guess I could have drawn R over here as well. Probably would have been better. Yeah, you know what? I'll draw another copy of R right here. That is also R. Okay, so from that diagram, right off the bat, there's a relationship that you might notice. If you look right here, we have ourselves a right triangle. We have ourselves a right triangle over there, which means I can actually get R as a function of L. It's equal to L times sine of theta. So already I can see that R is equal to L sine of theta. Another thing I haven't shown on my diagram is the force of tension. I think I'm going to draw that separately. So the force of tension points along that direction. If that angle is theta, then if that angle made with the vertical is theta, then this angle is 90 minus theta over here. Or I guess we could also say that this angle is theta. Yeah, I'll go with that. So force of tension points up at that angle, this angle being theta. And I'm going to go ahead and write the components of the tension force because we are going to need those as well. So components of tension, we're going to have a component to the right, which is force of tension times, let's see, it's not touching the theta, so it must be the sine, force of tension sine of theta. And for the vertical component then, that would be force of tension cosine of theta. I'm glad I have a variety of colors because otherwise this would have been confusing. In fact, it still looks a bit confusing the way I've drawn it. I want to write force of tension over here. Yeah, that's better. That reduces the risk of it being misread. And also, how do I want to separate these? Yeah, I didn't want to draw through my dotted circle over there. I wanted that to still be somewhat visible. Okay, so I think that's all the setup work we need to do with our diagram. So let me see what we were told again. So for part A, we are given the length of the string is 1.5 meters, and the mass is 0.5 kilograms. And the angle is 30 degrees, and theta equals 30 degrees. Determine the ball's speed. It's asking for v. Assuming this thing is moving in uniform circular motion, what would the value of v be? Well, if this is circular motion, then we need to have a net force pointing towards the center of the circular path. Our net force needs to be, in the case where the mass is over here on the left, the net force would have to be to the right. When the ball is over here, the net force would have to be, well, not down, but, like in this direction. And when the ball is over here, the net force would have to be in that direction. So wherever the ball is at any given moment in time, the net force has to be towards the center and only towards the center, which means net force in other directions would have to be 0. So I guess I'm going to need yet another diagram here. Well, actually no. For forces, I can just draw my force of gravity on this diagram. On this diagram, I'm going to have the force of gravity of the ball, or the weight of the ball, I should say, is just going to be straight down like that. And there you go, our force diagram is complete. So, obviously, there's not much point in analyzing every single point where this object could be. We can just pick one point and do the calculations for that point, and then for every other point it's just basically the same result, just rotated by however many degrees. So let's just go ahead and figure out what it would have to be when the ball is right here on the left. We would have to have a net force straight to the right. What forces do we have to the right? The only force we have to the right, according to our force diagram, is force of tension sine theta. So that's going to be our net force because it's our only force that's in the correct direction. We don't have any other forces pointing in the same or the exact opposite direction. We have two forces perpendicular to it. Those need to cancel out. So force of tension cosine theta must cancel with the force of gravity. So net force in the x direction, similar to our previous problem, is going to be, our centripetal force is going to be mv squared over r equals just force of tension sine theta. And net force in the y direction needs to be 0, equals force of tension cosine theta minus force of gravity is just going to be mg. I can add mg to both sides and divide by cosine theta to rearrange this into, let's see, if I add mg and divide by cosine theta, then I get mg over cosine theta is equal to the force of tension. I can take this and plug it in here. So this now becomes, let me switch colors for it. This now becomes mv squared over r equals mg over cosine theta times sine of theta. I can cancel the m's, and that gives me v squared over r is equal to g times sine theta over cosine theta is tan of theta. Not really important to rewrite that. You could just keep it as sine theta over cosine theta if you wanted, but if you recognize that it's equal to tan of theta, then that can help you just write it a little bit more compactly and save you a little bit of time from having to write both sine theta and cosine theta. It's 4 less characters that you would have to write down. And if you were given a multiple choice problem where you had to find the right expression, then chances are the correct answer choice would have it converted to tan theta, so you would want to be able to recognize that in case you have a multiple choice. But if you don't want to rewrite it and you don't have to, then don't. It's not exactly a crime. Anyway, now that I have this, I can solve for, they were asking for v, multiply by r, and take the square root. So if I continue this, I have v equals the square root of rg tan theta. I know r, well, I don't know r yet, but I do know it's equal to L sine theta, and I know L and I know theta, so actually that works. So v equals the square root of rg tan theta equals the square root of rg L. No, wait. No, replace the r with, hold on, let me erase that and try again. Equals the square root of r becomes L sine theta, so it's Lg sine theta tan theta. Okay, and now plug in the numbers. I could have plugged in the numbers a lot earlier because I knew the mass, but if you plugged it in, then you would have missed the fact that the mass cancels out. And besides, like I said earlier, if you're looking for more expression problems to practice, this is the way. Just don't plug in the numbers and there you go. If the problem had asked you instead to find an expression for v, then that's exactly what we did. So you have an endless supply of expression problems to practice. All you have to do is not plug in your givens. Square root of Lg sine theta. Square root of 1.5 times 9.8 times sine of 30 degrees. Oh, times tan of 30 degrees. Almost forgot that part. Times tan of 30 degrees. All that under the square root gives me 2.06. I'm getting 2.06 meters per second for part A. For part B, it says if instead the ball is revolved so that its speed is 4 meters per second, what angle does the chord make with the vertical? So now v is known, but theta is unknown. So part B, the length of the string, since they didn't mention it changing, it must still be 1.5 meters. They didn't mention the mass changing, although we've proven that the mass doesn't matter, but the mass is still 0.5 kilograms. Theta is unknown, but v is known. So v was given as 4. V was given as 4 meters per second. And the unknown this time is theta. Now, one of the other benefits of not plugging in your numbers too soon is that you can now reuse some of the work that you did in part A. You can now reuse some of the work that was done in part A. Let's see what has actually changed. So these relationships haven't changed. It's still true that the net force vertical has to be 0, and it's still true that the force upward is force of tension cosine theta and the force downward is mg. So that's still true, which means this is still true. It's also still true that whatever v is, mv squared over r is equal to force of tension sine theta, and since we know our vertical equation is still true, we can still replace force of tension with mg over cosine theta, so we can still get this result over here. We can still say v squared over r is equal to g tan theta, which means then that we can well, the r will have changed, so that's something we need to take into account. But we can start from this. We can start with this equation. And what do I want to do? Well, let me write it down, and then that'll help me kind of lay out what I'm thinking. Because I already know what's going to happen in my head, but putting it into words, I need to slow myself down a bit. So I can start from this and do v squared over r equals g tan theta rewrite this, multiply the r over, and this becomes v squared equals r times g times tan theta, or, as we wrote it earlier, L times g times sine theta times tan theta, because r gets replaced with L sine theta. So I can rewrite this as Lg times sine theta tan theta, And then what I want to do with that is actually rewrite the tan theta as sine theta over cosine theta. And the reason I want to do that is because when you're solving for theta, you need to get your trig functions and condense them all into a single trig function of theta. If I have sines and tans of theta, then I'm not going to have a good time trying to isolate theta. I need to get everything in terms of sines, or everything in terms of cosines, or everything in terms of tangents. One of those options. And I have a way of doing that if I rewrite the tangent as sine over cosine, because then I can do sine times sine is sine squared, and if you know your trig identities, then you know that sine squared can be rewritten in terms of cosine squared. You might remember that, I guess I'll write it up here somewhere. I'll write it over here. You might remember that sine squared of theta plus cosine squared of theta equals 1. Which means you can rewrite sine squared of theta as 1 minus cosine squared. So that's what I'm going for, but that's only the beginning of the manipulations that we have to do to get theta. So this turns into v squared equals LG sine squared theta over cosine theta. And I want to go ahead and multiply the cosine theta over, and let me actually grab a new sheet and continue this on the new sheet. So we have v squared equals LG sine squared over cosine. I'm going to multiply the cosine into the v squared. So I'm going to do v squared cosine theta equals, and then on the right hand side I had the LG, and I also had the sine squared theta. What I'm going to do with the sine squared is rewrite it as 1 minus cosine squared. So I'm going to rewrite this as 1 minus cosine squared of theta. And this is the part where a lot of people get stuck. How do I deal with, I've got a cosine theta term and a cosine squared theta term. How do I work with this? Well, if we go ahead and distribute and rearrange this, you might notice something about this equation. So I'm going to go ahead and say v squared cosine theta equals, if I multiply LG, if I distribute it, I get LG minus LG cosine squared maybe I should have divided the LG over instead. Actually, yeah, that's probably the better avenue. Let's divide the LG instead of distribute. I think it probably leads, no, it definitely leads to the same result, but I feel like this would be cleaner. V squared over LG cosine of theta is equal to 1 minus cosine squared of theta. And then what I want to do is move all this over to the left-hand side so that I get cosine squared of theta plus v squared over LG cosine of theta minus 1 equals 0. And from here, you need to make the clever observation that this is a quadratic equation. If theta is an unknown, then cosine of theta is also an unknown. You can say, for example, k is equal to cosine theta, or come up with some other letter, whatever you want, k, h, not L or G because we've already used those, q, u, whatever you like. And then if I rewrite this in terms of k, this is essentially just the quadratic equation, k squared plus v squared over lg k minus 1 equals 0, where you're solving for k. Your a is going to be 1, your b is v squared over lg, and your c is minus 1. So we can just use the quadratic formula here. I guess I'll start it off up here. K equals negative b would be negative v squared over lg, and then plus or minus the square root of b squared over 4a, or b squared minus 4ac. So that's v squared over lg squared minus 4 times 1 times c, which is negative 1, and then all over 2a, all over 2 times 1. Okay, from here we can actually start plugging in numbers to figure out which of our k's we want to actually use. So let me go ahead and grab my calculator, and we've got negative, let's see, v squared over lg. Let me actually calculate that separately because I'm going to need it in here too. So v squared over lg, we've got 4 squared over 1.5g. 4 squared over 1.5g. So 16 over 1.5 times 9.8. Don't forget to use parentheses if you're using the division symbol. If you're using the fraction mode on your calculator, then you don't need to worry about parentheses. And if you don't know what the fraction mode on your calculator is, then just use parentheses and be safe about it. 16 over 1 over the quantity of 1.5 times 9.8 gives me 1.088 approximately. So we've got negative 1.088, negative of 1.088, plus or minus, I'll start with plus, square root of that same number squared, 1.088 squared. Minus and minus cancel out, so that's plus 4. Whoops, that should have been in the square root, plus 4. There we go. And then all over 2 times 1, so all over 2. In the plus case, I get 0.594. And if I copy it and rewrite that same equation, and this time I use minus, I get negative 1.682. So 0.5, so I'm getting k equals 0.594, 594, or k equals negative 1.682. I can eliminate one of these right off the bat. I know it's not going to be correct. Which one is it? Well, remember, k is supposed to be cosine theta. So we can eliminate the second one because it's not possible for the cosine of an angle to be negative 1.682. Sines and cosines cannot give you numbers greater than positive 1 or lower than negative 1. They can't go above a 1, they can't go below a -1. So it's impossible for cosine theta to be equal to -1.682. If you try to do the inverse cosine of this number on your calculator, you will get an error, as you should. If you don't get an error, then check your calculator mode, make sure you're not... Actually, no, it wouldn't even matter if your calculator was in a different angle mode for this. You still would get an error. And if you don't, then either you typed something in wrong or your calculator is broken. Or programmed wrong because whoever manufactured it was trolling, but I think that's highly unlikely. So 0.594 it is. So cosine theta equals 0.594. So take the inverse cosine of 0.594 and you get 53.56. I'll just say 53.6 degrees is the value of theta. And that was part B. Wow, we've gone an hour and 15 minutes on just 2 problems, but hey, they're 2 really good problems. Anyway, part C says if the cord can withstand a maximum tension of 9.8 newtons, what is the highest speed at which the ball can move? So this time they are asking for V given that the force of tension is 9.8. For this one you actually need to know the mass, I'm pretty sure. So for part C, they tell you force of tension can be no more than 9.8, so just assume it's already maxed out at 9.8 newtons. Mass of the ball is 0.5 kilograms. If the mass of the ball was 1 kilogram or higher, this wouldn't be possible, because at 1 kilogram the weight of the ball would be all 9.8 newtons, so the tension would have to go to just preventing the ball from falling. And theta is unknown and V is unknown. We don't know theta, we don't know V. We do know the length of the string is still 1.5 meters for what it's worth. Okay, let's see if we can take a shortcut and reuse some of the math we did before. So because I don't know theta, I can't use this. And I can't use this because I don't know theta and I don't know r. I mean, r would just be L sine theta, but again, I don't know r because I don't know theta. So yeah, can't do that. If you have more than one function of theta, if you've got sine of theta versus tan of theta, then that's essentially the same as having 2 unknowns. If you have an unknown angle and multiple functions of that angle, then congratulations, you have multiple unknowns. So yeah, we can't do anything there. I guess we're just going to have to start here to solve for theta. Force of tension equals mg over cosine theta, so let's go ahead and use that. Force of tension equals mg over cosine theta. This will allow us to actually solve for theta, so force of tension 9.8 is equal to mass, which is 0.5, times 9.8, so the 9.8 cancels out nicely. over cosine theta. So cosine theta equals 0.5, which means theta would have to be 60 degrees. I know that because you're supposed to have your sines, cosines, and tangents of special or common angles memorized. Well, I mean, it's not required for physics courses, particularly the AP Physics course, because you get a formula sheet with that information on it. But I would still urge you to memorize that stuff, especially if you plan on taking calculus. Or if you are taking calculus. I don't know how you would get this far in calculus without getting the wake-up call that you need to memorize those, but just in case somehow you've made it through the school year without knowing those off the top of your head, you should know those off the top of your head. There's your wake-up call. Anyway, if I did just inverse cosine on my calculator of 1/2, then yeah, that gives me 60 degrees again. So in case you didn't know it off the top of your head, you can still use your calculator there, although I am deeply worried if that's your situation. Anyway, theta is 60 degrees. So now we can calculate V just using the formula that we had over here. V equals the square root of LG sine theta tan theta. So V equals square root of LG sine theta tan theta equals square root of 1.5 times 9.8 times sine of 60 times tan of 60 is about 4.6957. I'll say 4.70. 4.70 meters per second, which is okay, more than twice as much as what we got here, and still higher than the speed we were given in part B. So at least it's consistent with the previous parts. If the previous parts had speeds greater than 4.7, then that would have indicated to me that either the rope would have snapped in those first two scenarios, or string, or whatever they called it, or the maximum tension that the string can withstand is actually higher than what they told us in part C. But fortunately, that wasn't the case for parts A or B, so we can still assume that the maximum tension of this string is actually still 9.8 newtons. All right, now we can take a look at some gravitation stuff. So there was a problem that caught my eye while I was flipping around through the book looking for a banked curve problem. Which one was it? Yeah, it was this one. So it says, show that the escape speed from the surface of a planet of uniform density is directly proportional to the radius of the planet. Okay, let's do it. So I guess I should probably introduce some... Well, I mean, I'm assuming that you've already had some experience with gravitation and Kepler's laws if you're even watching this video in the first place. So I guess I don't have to go over that stuff. Let me just go ahead and review how we get escape speed. So if you remember, the gravitational potential energy in the universal perspective, some of you call it PE gravitational, some of you call it U gravitational, either symbol is fine. In the universal perspective, it's not mgh, it's negative gmm over r, where the zero of potential energy is usually chosen to be at infinity. You can write this as M1 and M2 or MA and MB. I like to use a big M and a little m because usually you're working with something like a big heavy planet versus a small, well, relatively smaller moon or satellite of some sort. Anyway, if we remember that formula, then we can use conservation of energy to figure out what's the minimum starting speed that you need to have in order to escape the gravitational field of a planet. And we can just write, well, let's see. So we would have to write mechanical energy final equals mechanical energy initial, assuming we don't waste anything against friction or air resistance. We would just say that negative g m over r final plus 1/2 m v final squared equals negative g m over r initial plus 1/2 m v initial squared. We notice that the little m cancels out everywhere. Little m cancels out everywhere. So the mass of the thing that's being launched does not even matter. Also, if you're trying to escape the gravitational field of something, then we would assume that you're trying to get far enough away from it that the gravitational force it exerts on you is zero. And the closest you'll get to zero is to get as far away as possible. So basically your r goes to infinity, and if you're dividing by a very large r approaching infinity, this whole thing is expected to go to zero. Also, if we're talking about just the bare minimum speed, if you want an initial speed that is just the bare minimum to give you enough energy to get here, then if you're only putting in the bare minimum, you should have no energy left over at the end. So if you have any kinetic energy left, then you went faster than the escape velocity, which is fine, I guess, as long as you escape. But we're trying to calculate what the minimum needed is. So we want to assume that you have no leftover energy either in the form of kinetic energy. So that makes that whole left-hand side equal to zero. And we can add gm over r initial after we recognize that r initial is just going to be the distance between the object and the center of mass of the planet before it's launched into space. What is that distance? That's the radius of the planet. So r initial equals the radius of the planet, and this v initial is the escape velocity we're trying to calculate. So add gm over radius of planet to the left-hand side of the equation and multiply by 2 to get rid of that fraction and take the square root. So let's see, one step at a time, gm over, I'm just going to call it big R, the radius of the planet, equals 1/2 v initial squared, which is actually our escape velocity that we're trying to calculate. Multiply by 2 and take the square root. So 2 gm over r square rooted is our escape velocity. Okay, But that's not what they're asking us here. What they're asking is show that the escape speed from the surface of a planet of uniform density is directly proportional to the radius of the planet. Here, we can't see that. Here we've got, based on this alone, it looks like it's inversely proportional to the square root of the radius of the planet. So the key here is the fact that they bring up density. If the planet has uniform density, if we know what that density is, let's call that density rho, Greek letter rho. I know it looks like a P, but it's kind of, well, at least I try to slant it when I write it. I know in some textbooks it doesn't look that way. They just kind of write it like this, and there's just a way that it's written in textbooks where you can tell it apart from a P, but when I write it by hand, I give it a little slant, and I also let it kind of stick out over here so that you can tell it's not quite the same as a P. Greek letter rho is typically used to represent volume density. So density, if an object is uniform, is equal to its total mass over its total volume. I should probably call that VOL, volume, so that it's not mistaken for speed. And the volume of a planet, if we assume the planets are spherical, then the volume would be 4/3 pi r cubed. That's the volume of a sphere. You remember the formula for a volume of a sphere, don't you? A lot of students forget these formulas from geometry. Volume and surface area of a sphere. So density is equal to mass over 4/3 pi, and then I guess this would be the radius of the planet cubed. So in other words, you can say that the mass of the planet is equal to this density times 4/3 pi r cubed. So density times 4/3 pi r cubed is equal to m. If we make this substitution into here, then we can see that escape velocity is 2 times big G times 4/3 rho times pi times r cubed over r, and I guess I didn't make the square root big enough to include that denominator. There we go, that's better. Reduce the r by 1 power, and you've got, I probably should have written v escape over there. V escape is equal to, the 2 and the 4/3 I guess becomes 8/3, and then, yeah, I'm going to write this as the square root of 8/3 pi big G rho, and then r cubed over r becomes r squared. And the square root of r squared is just r. And that's what they were looking for, right? Yeah. Square root of r squared is just r, so escape velocity is equal to the square root of a bunch of constants, is what it boils down to. Times r. Escape velocity is directly proportional to the radius of the planet. Of course, the misleading part of this is that the conclusion would have you believe that the radius of the planet is the only thing to take into account. You might think, oh, well, now I can just compare two planets and the planet with the bigger radius is going to have the bigger escape velocity. Well, that's assuming that they have the same density, which is not very likely. So, yeah, don't read more into this than what it's actually telling you. The density of the planet still matters, so you haven't really simplified escape velocity as much as you might think. Alright, I've got about half an hour left. What do I want to do with this half hour? Well, I guess I could continue with the density trend. I could continue with the trend of talking about density, because that's something that trips people up a lot when it comes to the topic of gravitation. I don't have any good ones in this book, I don't think. You would think, given how much I use this book to teach my students, I would know every single problem in here like the back of my hand, but there are a lot of problems in here that I don't think I've ever looked at, just because most of the other problems have been sufficient. My go-to problems are already among the most important ones to cover. Yeah, I think I'm just going to make up my own here. So let's say we've got planet Earth. I'll draw some random continents that don't even resemble what we have in real life, but let's say we've got planet Earth over here. And let's say that I want to have a satellite orbiting around Earth at an altitude of 2 times Earth's radius. So that's 1, and that should be about 2 Earth radii. 2 times the radius of Earth. And of course, the radius of Earth itself, maybe I'll draw it in a different color so it's easily seen. That would be 1 Earth radius right there. I guess I actually drew this bigger than 2 Earth radii, but it's close enough. So let's say you have a satellite that's orbiting around Earth at an altitude of 2 times Earth's radius. That is a very poorly drawn circle. That's a little bit better. And I want to find the force of gravity acting on this satellite in terms of the force of gravity on the surface of the Earth. But let's add the twist that I also want to find other things in terms of the force of gravity on the surface of Earth. So let F0 be the force of gravity, or actually, wait, the acceleration, hold on. Yeah, the force. let F0 be the force of gravity on this satellite, the force of gravity on a satellite on Earth's surface. On Earth's surface. Whatever the mass of the satellite is, we're not going to worry about it. We're just going to say that it's the same satellite for all the examples that I'm going to discuss. For all the cases, it's the same satellite with the same mass, but we're asking what force will act on it at different positions around different planets. So first off, when the satellite is on the surface of Earth, before we launch it, it's going to experience a force of gravity F0. What's the force of gravity it experiences when it is launched to an altitude of 2 times the radius of Earth? And then also I'm going to ask, what is the force acting on it if it finds itself on the surface of, let's say, planet X, whose radius is 2 times the radius of Earth? And I guess I didn't really draw this one to scale properly, but I tried. Assuming that planet X has the same density, and then if it flies at an altitude of, let's say, 1 Earth radius, or not flies, but you know what I mean, orbits at an altitude of 1 Earth radius, what will the force on it be then? And this assumes that the density of planet X is the same as the density of Earth. I'll talk about those details a little bit more after I'm done drawing. And then I want to also look at planet Y, which is going to be, I guess I'm going to make planet Y how about we make it how about we make it half as big? So if I make planet Y, and let's do it in a different color also just to keep it distinct. Let's say I make planet Y half as big as Earth, so, well, not half as big, but half as much of a radius, so I guess something like that. And then that radius is going to be 1/2 radius of Earth. And let's say we put the satellite on the surface of planet Y, but also we want to try putting our same satellite at, how about an altitude of 1 Earth radius? How about we put it at an altitude of 1 full Earth radius? Yeah, something like that. And I'll define a density for it later, but let's go ahead and actually do the first two parts. So, actually, let me do this ahead of time. So, planet X, I'm going to say density of planet X is equal to density of Earth. And I'm going to say that the density of planet Y is equal to, how about we make it 1.5 times denser than Earth, so 3/2 the density of Earth. I'm probably going to regret using so many fractions with planet Y, but I think that's what makes it a good practice problem. Okay, so let's go ahead and grab a definition for F0 in terms of Newton's law of universal gravitation. So let's do F0 is equal to the big G times the mass of the Earth times the mass of the satellite over, I guess that would be the radius of the Earth squared. Okay, perfect. Now we want to figure out what multiple of F0 each of our other scenarios are. If the satellite is at an altitude of 2 Earth radii above the surface of Earth, what is the force on it in that scenario? So at 2 Earth radii over here, the force on the satellite would be equal to big G times the mass of the planet is just the mass of Earth again, times the mass of the satellite, whatever it is, it's the same as before, over the distance between the center of mass of the satellite and the center of mass of the Earth is 3 times Earth's radius. It's 2 Earth radii away from the surface, which itself is 1 more Earth radius away from the center. So that total is 3 Earth radii, and then that needs to be squared. And if we square that, then the 3 also gets squared, so we're left with a 9 over there. And if I factor that 9 out, I'm left with 1/9 times big G, mass of Earth, mass of satellite, over radius of Earth squared. All of that stuff is equal to F0, so this is just going to be 1/9 as much gravitational force. That wasn't too bad. Now let's take a look at planet X. First, let's look at the surface of planet X. So on the surface of planet X, and I'll switch colors, I guess I'll do green since I drew planet X in green. On the surface of planet X, force is going to be big G times the mass of planet X times the mass of the satellite over the radius of planet X squared. The radius of planet X is 2 times the radius of Earth. So we've got that part down. But what is the mass of planet X relative to the mass of planet Earth? If it has the same density as Earth, it's got the same mass per volume as Earth, but it has twice the radius, then it has more volume. How much more volume? Well, if you double the radius, so volume of Earth, assuming Earth is a perfect sphere, is 4/3 pi times the radius of Earth cubed. The volume of planet X, and I guess I should have called it vol instead of v so that it's not confused with speed, but speed isn't mentioned in this problem anyway, so I guess we can get away with it for this one. V of planet X is equal to 4/3 pi times the radius of planet X cubed, so that's going to be 2 Earth radii cubed. And if I cube a 2, then I'm going to get an 8. So this is actually equal to, I'll pull the 8 out to the front, 8 times 4/3 pi radius of Earth cubed equals 8 times the volume of Earth. I guess I should have just kept it as an E instead of writing out the whole word Earth. Yeah, that's what I'll do here. So it's got 8 times the volume of Earth. And if the mass of planet X per unit volume is the same as it is for Earth, then mass of planet X is simply density of Earth times volume of planet X. So I can do, I guess I'll write it up here. Mass of X equals density of X times volume of X equals density of Earth times volume of X, which is 8 volume of Earth. Density of Earth times volume of Earth, though, is the mass of the Earth, assuming the Earth is uniformly dense. So mass of Earth times volume of Earth can be replaced with mass of Earth, so this just becomes 8 mass of Earth. If it has 8 times the volume under the same density, then it has 8 times the mass. Okay, and now that we have that, we can make the replacement in here. So F is equal to, this is going to become 8, and then big G and mass of Earth. We replace mass of planet X with 8 mass of Earth. Mass of satellite is still the same. Over, if I square the 2, then I have 4, and then radius of Earth squared. I don't know why I used parentheses for that. G, mass of Earth, mass of satellite over radius of Earth squared, that's just F0 again. And 8 over 4 reduces to a 2, so this is 2 times F0. So that would be over here. When you're on the surface, you experience a force of 2F0 for that same satellite. Okay, what about when it's out here? Well, when the satellite is out there, the numerator stays the same. It's still G times the mass of planet X, which is 8 times the mass of Earth, times the mass of the satellite. All that stays the same. The denominator changes. Now you are 2r plus 1r is 3 Earth radii away. So you've got 8g mass of Earth, mass of satellite, over 3 radius of Earth, all squared. If I square the 3, that becomes a 6. So 8 over 6, and then the rest is just F0 again. 8 over 6 reduces to 4 over 3, so 4/3 F0 when your satellite is at this point. Okay, I guess I should start circling my answers. So I got 1/9, I got 2, and now I've got 4/3. Okay, now to planet Y. On the surface of planet Y, what is my force of gravity on that satellite? If it lands on the surface of planet Y, what gravitational force will it experience? We were told that planet Y has 3/2 the density of Earth. So let's see, volume of planet Y, if it's got 1/2 the radius of Earth, then how much the volume of Earth does it have? It would have, well, for Vy, I guess I'll write it down here. Is that part of the screen still visible? Yeah. Over here I'll write Vy is equal to 4/3 pi. The 4/3 pi part doesn't even really matter all that much. And then 1/2 radius of Earth cubed. 1/2 cubed gives you 1/8. So planet Y has 1/8 the volume of Earth. Okay, that's all good. But for the mass of planet Y, I need to multiply by the density of planet Y. I need to multiply this volume by the density of planet Y. So where do I want to write this? I kind of don't want to bring out a whole new sheet of paper just for these last two calculations. I guess I'll do it over here. Yeah, this should be fine. So mass of planet Y equals density of planet Y times volume of planet Y equals 3/2 density of Earth times 1/8 the volume of Earth. Density of Earth times volume of Earth is mass of Earth. So that just leaves 3/2 times 1/8 is 3/16 equals 3/16 the mass of Earth. So even having a higher density than Earth doesn't make up for the fact that it's got half the radius. It's just got so much less volume that it's lacking in terms of mass. But now that we know that, we can go ahead and calculate force of gravity on the surface. So it would be, I guess I'll write it down here. I don't think I have the space for it, but I'll try. Force is equal to big G times 3/16 mass of Earth. So 3/16 big G mass of Earth, mass of satellite, over the distance when your satellite is right here on the surface. Its distance from the center of mass is just the radius of planet Y, which is 1/2 the radius of Earth, so over 1/2 radius of Earth squared. Okay, and if you square a 1/2, it becomes a 1/4. 3/16 divided by 1/4 is the same as 3/16 times 4, which is 12/16, which is 3/4. So this reduces to 3/4 of F0. 3/4 of F0. So that's what we have over here. 3/4 of F0 experienced on the surface of planet Y. And finally, when you are, what did I call that? 1 Earth radius in altitude above planet Y. So I guess I'll mark it here. What is the force at that location? Numerator stays the same. I guess I will cram it all into this last bit of space that I have, and maybe switch colors for this. Pink. So the numerator stays the same. We've still got a planet with 3/16 the mass of Earth and the same satellite mass. So numerator is still the same as before, but now the denominator is, let's see, we've got half an Earth radius plus a full Earth radius equals 3/2 of an Earth radius, and that needs to be squared. If I square the 3 halves, I get 9 over 4. 3 over 16 divided by 9 over 4 is the same as 3 over 16 times 4 over 9. So 3 over 16 times 4 over 9. 4 is reduced, 4 and 16 reduce, so that's a 4. 3 and 9 reduce, so that's a 3. So I'm getting, it looks like I'm looking at 1/12. So this expression amounts to 1/12 of F0. So over here, my satellite experiences a force of 1/12 the gravitational force it would experience on the surface of the Earth. And if you want more problems like this, all you have to do is experiment around. Just make up a bunch of different planets with a bunch of different radii relative to Earth, or you don't even need them to have radii relative to Earth. You can say that F0 is the force of gravity on the surface of planet A, and then say planet B has, I don't know, X times the density of planet A and Y times the radius of planet A, and calculate what the force would be at different altitudes or on the surface of planet B. And there you go. You can just throw around numbers and do calculations based off of that. If you want to make it even more interesting, you could also ask yourself to calculate, using Kepler's third law, you could ask yourself to calculate things like the period of orbit relative to the radius of the orbit. You could do those kinds of calculations too if you wanted to add yet another twist to this sort of problem. You could use that whole t squared over r cubed equals t squared over r cubed relationship to figure out what the period of the orbit of a satellite would be for planet A versus planet B. Well, actually no. If you have 2 satellites orbiting one of those planets, you could calculate the orbital period of one of them relative to the other. Or I guess you could also just do it for a single orbital radius around 2 different planets. Although in that case you wouldn't be able to use the t squared over r cubed equals t squared over r cubed version of the equation, because the planet being orbited would change. I guess you'd have to use a different form of Kepler's third law then. But you don't have to have Kepler's third law memorized. All you have to do is put together the universal gravitation equation with your centripetal force equation and replace velocity in your centripetal force equation with, velocity would be the circumference of the orbit divided by the period, and rearrange that and solve that for the period, and you would have Kepler's third law, which is a derivation that I would recommend practicing. So that's another thing that you can look at. But I think that will be it for today. I think I've rambled on long enough. I thought I was going to cover more problems than this, but I guess I just ended up picking some of the longer problems, and maybe I rambled a little bit too much on some of them, but I don't know. Different people are looking for different things here, and if you're looking for speed, I'm not the right person for that. I'm someone who values thoroughness very highly, and if you also value thoroughness, then you've probably come to the right place. But yeah, that'll be it for today. I'm not entirely sure what I plan on covering next week, but I'll have something figured out by then, like I always do. And again, if you have specific questions that you would like me to go over and I don't seem to be covering the topics you want, come to the live stream and ask your questions in chat. And if it's something that I can actually feasibly do and something that you can actually communicate in chat, then we'll get right to that. But that's enough of me rambling, so yeah, take care, and I'll see you next week.